Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about engineering typology subject. So in that today I will discuss about the laws of wear. So already in previous sessions we have learned the importance of engineering typology and that the various types of friction, and then what are the types of wears, and then how to overcome this wear, how to reduce the friction. All these things we have discussed in the previous session. So in this today's topic we will see the laws of wear. So in this laws of wear, various laws are there. First of all, we should know the wear. Already you know the wear is the process leading to loss of materials is known as wear. So how much loss will be occurred during machining? That is called as wear. So this wear depends upon the type of material, and then type of operation, and then environmental conditions also. So this laws of wear, the Harchards, the scientist invented this law for abrasive wear. So in this Harchards law, the friction and wear, these two things are depend as much on sliding conditions. So sliding conditions means the normal pressure and the sliding velocity as on properties of materials concept. So already I told you this wear depends upon the properties of the material. So that these two, the friction and wear conditions, wear parameters depend on these sliding conditions. So what are the sliding conditions? One is sliding velocity, another one is normal pressure. So according to this Harchards law, the normal pressure and the sliding actions are necessary for wear. So that is the mechanical wear. So it is a result of the mechanical action. So whenever the two surfaces are in relative motion, so whenever there is a mechanical load, there is compulsory mechanical wear. So this, so in this, the two things are important. One is normal pressure and sliding action during the application of load. Therefore, the wear process depends on this rubbing process. So according to the rubbing conditions, the wear rate is there. So the earliest contributions to the wear constitutive equations were made by whom? So in 1946. So the Home established a relationship between these the volume of the material removed by wear, that is W, in the sliding distance, that is S, is related to the true area of contact. So the Home, according to the Home, this relationship between these two, the W and S, so that is sliding distance, and this is volume removed by wear. We will see that equation. So that is W is equal to K into Pn into S by H. Here in 1953, the Harchards formulated the wear equation of the form. So that is the volume of material removed, that is W, is directly proportional to the sliding distance. So that is the W is directly proportional to the sliding distance and the normal pressure. the normal pressure, and the dimensionless wear coefficient K. So that is we can write in next equation. So and then inversely proportional to the hardness of the surface being 1 by h. This is hardness. So we can write with the help of dimensionless wear coefficient, that is K into Pn into S by h. So here the K is the dimensional wear coefficient and depends upon the wear rate and the material properties. Next one is the sliding distance S, and then the normal pressure Pn. So the hardness of the surface that is inversely proportional, so that is H. So the wear also depends upon this hardness of the material. So you can represent with H. So nowadays it is generally recognized that the wear is related to the wear coefficient, the pressure and the sliding distance. So generally they recognize with the help of this wear coefficient, pressure and sliding distance. The wear coefficient K, and then pressure, and then the sliding distance. So, yes. So the pin on disc test experiments can be used to determine how wear is acted by the pressure and the sliding distance. So how much pressure acted, and then how much the mode and how much wear happened due to this sliding. The pin is sliding on this disc. So I will explain in later slides. So there is a equipment that is a pin on disc. This experiment, this machine is used to know the wear and friction properties of a particular material. So according to the Orchard equation, say W directly proportional to the wear rate and then hardness. So W, small w is normal load on contact, H is the surface hardness of the wearing material, K is the wear coefficient, that's dimensionless. So W is equal to K into W by H. So here wear coefficient K by H is called dimensional wear constant, and then unit is volume per load per meter. So you can write this W, the wear, normal load and contact in terms of wear and the wear coefficient, you can write like this. So now come to the pin on disc test. So pin on disc wear test is carried out according to the ASTM G99 standards. So this is according to the ASTM standard, this the test carried. The parameters used in this pin on disc are, the first one is load and sliding velocity and sliding distance. So in this figure shows the pin on disc operators. So pin on disc operators, the disc is here. So and then the pin shown here, and applied load is here. So in between this polymer block is there, and then wear track. So this is wear track. So in this, the pin slides on this disc. So whenever this disc starts to rotate, so then immediately this pin also moves in sliding way according to the applied load. So after some time, there is a wear between this pin and disc. The disc material is separate, and then pin material is separate, different. So the pin on disc tests are preferably used to determine two body sliding wear. So in pin on disc, the pin is attached with the polymeric material, already shown in diagram. That is slide against the metallic disc or the metallic pin is slide against the disc made of polymer material. The disc also made of polymer material. The spin slides on this the disc. So next, theoretical wear models. Uh, the theoretical wear models are mathematical or computational frameworks used to describe and predict the mechanisms and rates of material removed due to wear. So it describes the theoretical model, the wear model, predicts the mechanism and the rate of material, how much material removed due to wear you can calculate. So in previous case in pin on disc test also we can calculate the wear rate and then friction rate of the particular material. Like this you can calculate different materials properties. So finally for research purpose you can suggest a good material. So in this, these models are developed based on the fundamental understanding of the physical and the chemical process involved in wear. So developed based on the fundamental understanding of the physical and the chemical process involved in wear. There are essential tools for engineers and researchers to design, optimize, and troubleshoot systems subjected to wear. So in this, essential tools for the researchers are design, optimize, and troubleshoot systems that is subjected to wear. These are called as theoretical wear models. Now, some common theoretical wear models are, so I will explain. First one is Orchard's wear law. So in Orchard's wear law, is one of the fundamental models used to describe wear in sliding content. Already have discussed in the previous slides. It states that the wear volume is directly proportional to the normal load, sliding distance, and a material dependent that is constant is called the wear coefficient, that is K. So the wear volume is directly proportional to the normal load, so that is W, directly proportional to normal load W and the sliding distance. That is, you can write a normal load in terms of Pn, which is Rs, is inversely proportional. So next, adhesion and abrasion models. These models focus on the adhesive and abrasive wear mechanisms. We have studied in earlier sessions. So what do you mean by adhesive and abrasive wear mechanisms? So which involve material transfer and removal due to surface interactions between two contacting bodies. So there is a material removed due to the surface interaction with each other. They often incorporate parameters such as surface roughness, contact pressure, sliding velocity to predict wear rates. Next, erosion models. So erosion wear models describe the material removal caused by the impact of solid particles or liquid droplets on a surface. So they consider factors such as particle size, velocity, angle of impact, and the material properties to predict erosion rates. So the erosion wear models actually it describes the material removed. So due to the impact of solid particles or any fluid droplets on a surface. So this you can predict the erosion rate, that is depends upon the factors of particle size and then velocity and angle of impact. Next, fatigue wear models. The fatigue wear occurs due to cyclic loading and can lead to surface cracks and material swelling. So already know the fatigue wear. So whenever when a component subjected to cyclic loading, so it means the repeated loads. So whenever this component is subjected to these type of loads, it leads to the surface cracks and then material spalling. This phenomena is called as fatigue, and due to this fatigue, some wear is there. That wear is called as fatigue wear. So the fatigue wear models consider factors such as stress amplitude and the number of cycles and the material properties to predict fatigue induced wear. So this fatigue the mainly depends upon the stress amplitude. So how much the stress acted, how much load acted on that particular component, and how much number of cycles this component occurred. So that is observed. So after some cycles, after some number of cycles, the component will fail due to yield stress. Clear. So then the fatigue fracture will be occur in the component. So like this, by using this fatigue wear model, you can predict the fatigue induced wear. Next one is the tribochemical models. So tribochemical wear models incorporate chemical reactions between contact surfaces. So the contact surfaces, whenever in contacting or whenever in relative motion, there is a chemical reaction between these two surfaces. The chemical reactions are oscillation, corrosion, and formation of protective films, which can influence wear rate. So these models often consider parameters such as temperature, humidity, and the chemical composition of the contacting materials. So these are the parameters important when considering this tribochemical models. Next is wear particle generation models. So in this type of systems, where particles are generated, such as in lubricated contacts, models are used to predict the size distribution, shape, and then concentration of wear particles based on parameters such as contact geometry, lubricant properties, and operating conditions. Based on these parameters, it depends upon this wear particle generation model. Naturally, it predicts the size and the shape and the particle distribution. Next one is wear map models. The wear map models categorize wear regimes based on the dominant wear mechanisms. Example: adhesive, abrasive, and fatigue. And then the parameters such as contact pressure, sliding velocity, and the temperature. These maps help in selecting appropriate materials and lubricants for specific operating conditions. So based on this type of wear mechanisms, so it may be adhesive or abrasive or fatigue, and many other mechanisms also there, like erosion mechanism. So this is comes under the wear map model. Let's say 8.1 finite element analysis (FEA) and then the computational fluid dynamics, that is CFD. These two are simulation process. So generally used in mechanical components to know the stress distribution and flow properties. So these simulations are often used to complement this theoretical wear models by providing detailed predictions how stress distribution, fluid flow, and temperature gradients, and the temperature gradients and complex geometries, it influence wear behavior. So these two also comes under some theoretical way models. This is finite element analysis and a computational fluid dynamics model. So these theoretical wave models are continuously refined and validated through experimental observations and measurements to improve their accuracy and applicability across various industries and applications, so that you can optimize the various design parameters. So based on these observations. Clear? Next topic is wear of metals. So in this the wear of metals, abrasive wear. So metals can experience abrasive wear when subjected to the rubbing or scraping of hard particles against the surface. So whenever there is a rubbing between the two surfaces, so there is a abrasive wear. So this type of wear occur in machinery components that come into the contact with abrasive materials or environments. So next, adhesive wear. So the adhesive wear in metals involves the transfer of material from one surface to another due to high contact pressures and temperatures. So this can lead to localized welding between the surfaces, followed by material tearing upon separation. So this sometimes that's why this type of joint is called welded joint due to the adhesive property. Next, erosive wear. So materials can undergo erosion wear when exposed to the impact of solid particles and liquids or gases. So this is common in industries such as mining and manufacturing industries. So where high velocity fluids or abrasive particles cause surface degradation. So many times exposure to impact loads, impact of solid particles, and sometimes exposure to the liquids and gases also. So due to this type of exposure, so some material will be lost. This type of wear is called erosive wear. Next one is fatigue wear. Already I have studied. It occurs in metals due to the repeated cyclic loading or stress leading to the formation and propagation of cracks. This type of wear is common in components subjected to dynamic loading, seen in mechanical components like gears and springs. Next, corrosive wear. The corrosive wear results from the combined action of corrosion and mechanical wear. So metals exposed to corrosive environments can experience accelerated material loss due to chemical reactions, weakening of surface, making it more susceptible to mechanical wear. So this type of wear happen due to the combined action of corrosion and mechanical wear. Fretting wear. So fretting wear occurs in metals due to slight relative motion between contacting surfaces, often caused by vibration or oscillation. This can lead to localized surface damage and material loss. Next, similarly, the non-metals, the wear of non-metals. The same as metals, the proper ways, but here we will consider non-metallic materials. So like polymers, ceramics can experience abrasive wear when subjected to abrasive particles or surfaces. So this can lead to the gradual removal of material and surface degradation. Next, adhesive wear. The adhesive wear in non-metals involves the transfer or removal of material due to high contact pressures and temperatures. So this can occur in applications where non-metallic materials come into the contact with each other under sliding or rolling conditions. This type of wear is adhesive wear in case of non-metals. So next one is erosive wear. So non-metallic materials can undergo erosive wear when exposed to the impact of solid particles, liquids or gases. Some industries, this type of erosion wear happen. So this is common in applications such as erosion of polymers in pipelines carrying abrasive slurries. Next, fatigue wear. So while less common, some non-metallic materials can experience fatigue-like wear under cyclic loading, leading to crack information and eventual failure. This can occur in polymers and composites subjected to repeated mechanical stresses. So whenever the object, the component is subjected to repeated mechanical stresses, there is a fatigue wear. Next, corrosive wear. So non-metallic materials may degrade due to chemical reactions with their environment, leading to a loss of mechanical properties and eventual wear. So this is particularly relevant for polymers exposed to harsh chemicals or UV radiation. Next, fretting wear. Same as metals, but the fretting wear in non-metals can occur due to the slight relative motion between the contacting surfaces. This leading to surface damage and material loss. This is especially relevant in applications where polymers or composites are used as seals or bearings. So understanding this type of wear mechanisms for both metals and non-metals is crucial for designing materials and components with improved durability and performance. So whenever if you want to design any component in a mechanical machine element, you should understand the wear mechanisms of both the metals and non-metals. So based on the properties you can design. You can improve the durability and the performance of the component. So the strategies to mitigate wear include selecting appropriate materials, surface treatments, and lubrication. Proper lubrication is required, and then design optimization to minimize wear-related issues. So how wear-related issues you can minimize by following these type of strategies. So you can think for a better material. So you have to select a proper design, how to select a proper operation. So you have to select design parameters. All these strategies leads to minimize the wear related issues. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.